the pulse of blinding light, the red-hot fireball, and the column of superheated gases rising miles into the atmosphere as it rains down radiation below. These are the events that unfold after the detonation of an atom bomb. In this video, I'll take a closer look at each stage of this catastrophic event and understand what happens and why. This is the dark science of a nuclear explosion. In detonation, a subcritical mass of either uranium-235 or plutonium-239 is imploded by a chemically initiated explosion. This explosion condenses the radioactive core into itself, creating an unstable supercritical mass. When struck with a neutron, this supercritical mass detonates. When a radioactive nuclei is struck with a neutron, it splits into radioactive isotopes and free neutrons. These neutrons then strike other nearby radioactive nuclei, causing them to split and release neutrons, thus creating a chain reaction. However, if the density of the uranium core is too low or subcritical, neutrons will strike very few nuclei as they are too spread out. As a result, a chain reaction cannot occur. This is why just before the core is shot with neutrons, it's forcefully imploded into itself. Implosion increases the density of the core, pushing the nuclei closer together to make a chain reaction more conducive. When the density of nuclei is high enough to cause a chain reaction, it's known as a supercritical mass. The energy from the kinetic split of atomic nuclei releases an immense amount of energy, so much that electrons are energized to the point of emitting several bands of electromagnetic radiation. This emission consists of visible light, ultraviolet light, X-ray, and gamma rays, and appears as a pulse of blinding light that lasts for 1/10 of a second. Emission of light by excited electrons is called spontaneous emission, and is a known phenomenon. Whenever electrons absorb energy, they jump to a higher energy orbit in their atomic arrangement, and then return back to a lower orbit. While doing so, they emit a form of radiation, often between infrared and gamma rays. For example, when you pass electricity through a tungsten filament in a light bulb, the temperature of 4,600 Fahrenheit causes emission of visible light from the electromagnetic spectrum. The more energy the electron absorbs, the higher frequency radiation it emits. For example, the heat from splitting a radioactive nuclei is over 100 million degrees Fahrenheit. This temperature excites electrons so much that they emit UV, X-ray, and gamma radiation. That is initially 2.5 times brighter than the sun. The intensity of this radiation can cause flash blindness and burns to the eyes and skin. This is footage from Operation Upshot Knothole Grabble, where a 15 kiloton atom bomb was detonated. This Army vehicle was placed approximately 3,000 feet, or a little over half a mile from ground zero. Upon detonation, heat from the emission of high-energy X-ray and gamma radiation vaporizes the paint off the vehicle. This illustrates just how destructive it is to human skin. Little Boy had a blast yield of 15 kilotons, yet it still caused significant burns as far away as 2.5 miles from ground zero. The sustained splitting of atomic nuclei produces temperatures and pressures comparable to the interior of the Sun, in an area no longer than 10 feet. Air is quickly ionized, creating a superheated plasma, producing a massive fireball that expands to a diameter of half a mile. A spherical fireball is formed because explosions expand equally in all three dimensions, forming a ball of superheated plasma. Heat from the expanding fireball causes air around it to rapidly heat up and expand outward at supersonic speeds. The front of the blast wave, called the shock front, moves a wall of compressed air at speeds of 780 miles per hour, destroying and throwing anything in its path. The initial shock wave weakens structures and disperses air in the immediate area, causing a void. The surrounding air then rapidly rushes back in, which tears the weakened structure to pieces. The compression, vacuum, and blast winds together may exert forces stronger than a level 5 hurricane. Research from Japanese surveys after the Hiroshima and Nagasaki events found that winds traveling at roughly 294 miles per hour was enough to destroy wooden buildings, severely damage cement structures, and cause human lungs to collapse. After the fireball deforms into hot gases and fiery clouds, the heated mass rises as it's less dense than the air around it, similar to a hot air balloon. However, there are denser gases above the heated gases that are trying to rise. As the heated gases ascend, they cause turbulent mixing with the more dense gases, and pull the denser gases upward with them. This creates the stem of the mushroom cloud and is known as Rayleigh-Taylor instability. This occurs when a high-density fluid and a low-density fluid mix together. The clouds at the top have low density, while the clouds in the stem are more dense. The cloud itself has a red hue from formation of different oxides of nitrogen, as the heated gases readily react with nitrogen in the air. The heated gases climb at a rate of about 300 feet per second, eventually reaching a ceiling of 4 to 6 miles in roughly 10 minutes. At about 5 miles in the atmosphere, temperatures reach as low as -35 degrees Fahrenheit, where water vapor condenses into clouds. The hot gases lose kinetic energy and condense into water droplets, shifting the red hues to a grayish white, producing the characteristic mushroom cap at the top of the column. With no more heat left to rise, the cloud diffuses horizontally in the atmosphere. As the mushroom cloud cools and diffuses in the atmosphere, radioactive isotopes from the fission reaction descend back to the ground. Nuclear fission of plutonium and uranium produces over 300 radioisotopes. However, common products are strontium-90, cesium-137, xenon-135, iodine-131, and barium-141. Some isotopes, though radioactive, are not a major threat due to short half-lives. For example, the half-life of barium-141 is 18 minutes, and xenon-135 is 9.2 hours. Some have longer half-lives and therefore pose a serious threat. Iodine-131 has a half-life of 8 days, which is moderately long, but is nothing compared to strontium-90's half-life of 29 years, or cesium-137 of 30 years. These longer half-lives pose a serious risk, as the radioactive material stays present for decades, increasing the chances of cancer exposure. But even these radioisotopes don't have the longest half-lives. Despite the magnitude of the nuclear explosion, only a small amount of the fissile plutonium-239 and uranium-235 was used up. Batman contained 13.6 pounds of plutonium, but only 2 pounds or 14% underwent fission. Likewise, Little Boy contained 140 pounds of uranium-235, with 2.4 pounds or 1.7% undergoing fission. The remaining 11.6 pounds of plutonium and 138 pounds of uranium was vaporized and later fell to the ground with the rest of the fallout. Plutonium-239 has a half-life of 24,000 years, and uranium-235 a half-life of 700 million years. Cancer surveys conducted in Japan from exposure to fallout as late as 1958 found an increase in cancer rates, with stomach, lung, and liver cancers being the most common. The detonation of a nuclear bomb instills beauty, awe, and terror. The magnitude of energy and destruction that follows is a revelation of the power that lies in the world around us, and whether it be used for good or evil. Though the nuclear age has changed history, we still have yet to see what future it will bring. Thank you for watching Dark Science.